If we really think about it, water is everywhere. It's in plants, the air we breathe, the food we eat, and the beverages we consume. But why? What's so important about water? Let's find out together in this episode all about aqueous solutions. This coffee is 98% water. And then you have this soda and sports drink, which are about 90% water. And our bodies are about 60% water. Water allows our digestive system to transport nutrients into our bloodstream and carry them throughout our body. Plants need water for photosynthesis and to transport dissolved nutrients from their roots throughout their tissues. All of this is possible because water can dissolve more substances than possibly anything else on Earth, which is why water is sometimes referred to as the universal solvent. Solubility is a physical property of matter, which is the ability of matter to dissolve in another substance and form a solution. A solution is made up of a solute and a solvent. A solute is something that dissolves in a liquid, and a solvent is the liquid that something dissolves in. If you need a refresher on mixtures and solutions, you can check out this video. Today, we are going to be looking at aqueous solutions, or mixtures where water, the solvent, dissolves another substance, the solute. This sports drink is a solution. Water is the solvent, and the mixture of sugar, sodium, flavors, and coloring is the solute. Not all solvents are created equal. Water has the title of universal solvent because it can dissolve more substances than any other liquid. And to understand how this is possible, we need to observe what is happening down at the atomic level. So what's really going on when we dissolve something in water? For a solvent to dissolve something, the solvent has to pull apart the molecules that make up that substance and keep them apart. Water molecules are shaped like this. Because this large oxygen atom is really grabby for electrons, it has a slight negative charge, while this area with the hydrogen atoms has a slight positive charge. This makes water polar, kind of like a magnet. This allows water molecules to pull apart and get between other molecules, or pieces of molecules with charged parts. If we could somehow view the water in this beaker down at the molecular level, we would see the water molecules moving around. If we were to drop a salt crystal into the water would act as a solvent and the salt as a solute, like we learned earlier. The water molecules would then start to pull the sodium and chloride ions off. The positive side of the water molecule would remove the negatively charged chloride ion, and the negative side of the water molecule would attach to the positively charged sodium ion, just like a magnet, attracting opposite poles. The sodium and chloride ions would disassociate until they're completely dissolved, creating a perfectly mixed solution with water. A very similar thing would happen if we traded out the salt crystal for sugar. Instead of pulling ions off, the negative side of the water molecules would be attracted to the positive side of the sugar molecules. The water molecules would insert themselves between all of the individual molecules of the sugar that were once bunched together. Now, also a perfectly mixed solution with water. Just a side note, water doesn't dissolve all substances. It doesn't dissolve non-ionic, non-polar substances like oil, for example. Oil doesn't have any polarity, so it's unbothered by the water. That's why no matter how hard you try to mix them, they always separate. If you're still here liking this video, let us know, and hit that subscribe button so you never miss an episode. How fast a solute dissolves in a solvent depends on a few different factors. 1. Stirring or mixing action. 2. Surface area or particle size. And 3. Temperature. We are going to test each of these factors when creating an aqueous solution of sugar. Inside these two beakers, we have 100 milliliters of room temperature water. Inside this first beaker, we are going to add 5 milliliters of sugar without stirring or mixing. Inside the second beaker, we are also going to add 5 milliliters of sugar, and then we will stir or mix until there is no sugar crystals on the bottom of the beaker. Which beaker do you think will dissolve the sugar the fastest? Stirring helps to dissolve a solute faster by consistently bringing more solvent molecules into contact with the solute surface, increasing the rate of collisions that break the solute apart. Just like we saw in our stirring example, how fast a solute dissolves is mostly about how quickly the two different molecules or pieces of molecules can evenly occupy the container. If I were to drop a sugar cube inside of our water-filled beaker instead of granulated sugar, do you think the sugar cube would dissolve faster or slower? At this point, there's way more sugar in the sugar cube beaker than in the granulated sugar beaker. Let's keep stirring. There's still some sugar at the bottom of this beaker, so our granulated sugar dissolved faster than our sugar cube. Let's test again by changing the temperature. Inside of this beaker is cold water. We will add 5 milliliters of granulated sugar at a time until we can't add any more, because we will have a saturated solution with sugar crystals at the bottom. Okay, I think that's going to do it. I stirred so much, we're making a mess. We were able to dissolve 15 milliliters of sugar inside of our cold water. You can still see there's some granulated sugar here at the bottom. Now let's test hot water. Our hot water beaker was able to dissolve 45 milliliters of sugar. I'm glad that it stopped at 45 with still some sugar crystals here on the bottom, because my water level has increased so much that it's almost spilling out. Which makes sense, because all of this sugar is displacing the water. So the next time you're enjoying your favorite drink, remember to thank water, the universal solvent, for dissolving those solutes so well. And if you want to learn more science, you can check out this video next. Lettuce depends on a few different factors.